There, okay, now we are recording. All right, so if I can get you to go to the Google Draw page or the link that I sent in the chat today, we're going to be doing some history graphs. So the idea with this type of question is that I have given you, we'll start just with this orange one. Oh, I guess I can't click on it. We'll start with this first orange graph. And this is showing a wave, and it's plotted in the y-x plane. So we're looking at horizontal position versus vertical position at time t equals 0. And I didn't tell you what direction the wave is traveling in, so I guess I can do that now. This wave is going to have a speed to the right. We'll make that a little more visible. And the speed is going to be 2 meters per second. And I'll just write that in there so you have it. So at time equals 0, we have this orange wave traveling to the right at 2 meters per second. And what I want you to draw, and I've given you some orange lines on the left here that you can manipulate. What I want you to draw in one of these, pick whichever graph in this first row. I want you to draw what would the history graph look like at x equals 6. So we know what the graph looks like at this starting time. And what I want you to draw or create with these, with the lines that I've given you here, is looking just at a point at x equals 6, where my cursor is there. You could imagine maybe it's a bead on a string that's stuck at x equals 6. What would the movement or the trajectory of, I guess, the wave look like at this position? I'll give you a couple minutes to try that first. Try that on your own first. Play around with it. And then we can talk about it together in a minute. Feel free, if you have any questions, to put them in the chat, or feel free to say them out loud. That's great too. Okay, so question in the chat says, if there are 2 points at x, so here we're looking at the point x equals 2, where the shorter vertical line is, and x equals 4, where this kind of higher vertical line is. You know, these two different x values, they can't both occupy 1 point at x equals 6. Absolutely. So this wave that we're looking at, this, I don't know, it's kind of like a half a trapezoid shape. It won't be at x equals 6 all at the same time. So what'll happen is, as this wave is traveling towards the right, this taller vertical line will get to x equals 6 first. And then as it continues to move over to the right, this kind of slanted line part of the wave will go past x equals 6. And then lastly, this vertical spot will go past x equals 6. So what we're showing on the graph, on the y versus t graph, which is the history graph, as opposed to the y versus x, which is the snapshot graph. On the history graph, we're showing, or I guess we're saying, what would the wave look like over time at the point x equals 6. I'll give you a ready to continue message when you want me to turn my mic back on and kind of explain and talk through the answer. But do give it a try first, and yeah, let me know when you're ready to continue. And I guess one last thing I wanted to say, if there's any trouble with the technology aspect of this, let me know and I can try drawing it out or something. I have, because all of these graphs, I had to, like, I brought them all in, but I saved them just as a picture and I have it as a picture. So if that causes any problems for you, let me know. Oh, the orange lines won't go on the graph. Oh, it's putting it behind it. Let's try. I'll try putting the image in the back of the screen. Does that work? Oh, I see an orange line moving around. Okay, give that a try. Okay, I see a good guess here. So let's talk about this a bit. So what you've got in what the anonymous rabbit, what you have in your graph here. So you have the original wave and the same shape and the same proportions. It hasn't been stretched or squished or anything weird like that. And it's moved over so that it's lining up with 6 here. So what this would look like, what your graph is actually representing it's not the history graph at the position x equals 6. What you're showing is still, like, if this was a y versus x graph, when the wave starts to hit x equals 6 is what you've shown. But what we're trying to show is how the wave goes through x equals 6 as time goes on. So now we're focusing just on the motion of, like, we're focusing on the motion of just the point x equals 6. So I'll talk you through this one, and then we can try again with the next example. So I'm going to start by looking at the first kind of vertical line here. So this first, the first vertical line, or at x equals 4, it starts out at time equals 0. It starts out 2 meters away from x equals 6. And so starting out 2 meters away from x equals 6 means it's going to take 1 second to get to x equals 6. So since it's starting 2 meters away and it's traveling at 2 meters per second, you can think of the formula, I'll type it out just up here, as t equals v divided by x. Oh, except I have that backwards because those units aren't going to work out. Sorry, it should be x divided by v. So you can think about it kind of using this formula. Say, well, if it has to, so this first vertical line, it has to travel 2 meters to get to x equals 6, and it's going at 2 meters per second. So that means it'll take 1 second to get there. So looking at the y versus t graph, I'll do mine in the middle. The vertical line, which something like that. I guess that might be a bit big. So I'm going to put this line at t equals 1 because it takes 1 second for the point x equals 6. It takes 1 second for it to see the wave, or for the wave to get to that point. And actually, for visualization purposes, I'm going to click on the wrong thing, but now I'm going to add a little point at x equals 6. So there's the point on the string that we're looking at. As an example. And so for the wave to get to this point, it'll take 1 second to get there. And so on my y versus t graph, I have this vertical line at 1 second because we're starting at t equals 0, and so it took 1 second to get there. Next, we have, I guess we can look at this second vertical line and see how long, well, we can see how far does it take for this second vertical line part of the wave. How far does it have to travel to get to x equals 6? And we'll figure out how long that took and put that on the graph. So this this vertical line it starts out as 4 meters away from x equals 6. And so what we can do on our graph is say, well, if it took 4 meters to get to x equals 6 and it's going at 2 meters per second, that means it will have taken 2 meters. No, it will have taken 2 seconds for this vertical segment to get to the point. And so if it took 2 seconds for that second vertical segment to get to the point, I can put my second line here at t equals 2. It took 2 seconds to get there. And now between these two vertical segments is the kind of the slanted part of the wave that joins the two. And so I can kind of sketch that in, or I guess add that into my graph accordingly. So after 1 second, the this first kind of peak of the wave hit x equals 6. And so after 1 second, we have this maximum value here. And then it took 1 second for the wave to decrease until we get to 2 seconds. And that's where this second corner, like the second vertical segment is. And then after 2 seconds, as time gets bigger, and so that's going along this x-axis here, as time gets bigger, or like time goes on, I should say, there is no wave, because once this awkward shape wave goes by x equals 6, there's nothing else coming after it. So after 2 seconds, there's no wave. And so that would be the complete graph, history graph for this one. That makes more sense. Good. Okay. Let's try another one. Let's do this green one. This green one's going to be traveling to the left. And it's going to be traveling at, I don't remember if I made it. No, I do remember, never mind. It's going to be traveling at 3 meters per second to the left. So at time equals 0, this is what the graph looks like everywhere. And I just realized no, I didn't. Never mind. I thought I made a mistake and then I didn't. Okay, sorry. So this green triangle shaped wave is traveling to the left at 3 meters per second. This is what maybe it's on a string, a wave on a string. This is what the string looks like at time equals 0. What I want you to draw now is the history graph on one of the graphs in this second row here. Draw the history graph at x equals 1. So we'll add a point for that as well, or a bead on the string. We'll make it green to go with the rest of it. This green point on the string, or the bead on the string, what is the motion, or yeah, like what's the motion of this point going to look like? Because that's at x equals 1. What's that going to look like as the wave travels to the left? So go ahead, try sketching that on one of the these graphs that say x equals 1 in the corner here. Let me know if you have questions, and otherwise I'll give you a ready to continue message in the chat. Oh, sorry, I missed a question in the chat here. Is the right leg of the small green triangle at x equals 4.5? Yes, it is small, you're right. Okay. Each of the numbers written on the x-axis in the original graph are even numbers, and actually same for this t-axis. So this would be at, so here's 4, 5 would be this light line, so the end here would be at x equals 5.5. Thank you for clarifying that. Okay, so in the chat, you're asking, it's traveling away from x equals 6. Oh, okay, sorry. For this second graph, I didn't make it super clear. For this graph with the green triangular shaped wave, I want you to do the history graph for the position x equals 1. So we're looking at this dot here that the wave is traveling towards. You're absolutely right. If you were to do a history graph for x equals 6, you would have to look at like quote unquote negative time values because the wave has already passed completely through x equals 6. We'll actually get into that in the third example, but for this one, just do the graph for the position x equals 1. Okay, and looks like we're ready to talk about this one. So this graph looks really, really good. Okay, so I'm gonna follow along with yours and I'll do mine here. So you're starting your graph, you're starting it right at the origin, which absolutely it should be, because at time equals 0 on the snapshot graph that we're starting with, the wave has like just reached the point. So the point's going to start going up right away. Absolutely. And so now looking at this first vertical segment, for example, this has a peak at, well, I guess it's, I'm going to be a bit lazy. I'm just going to say 1, 2, 3 squares over, which ends up being 1.5 meters, like meters wide, I guess, meters over. And so if it's traveling at 3 meters per second, and it has to, like the wave itself has to traverse a distance of 1.5 meters to reach the peak. excuse me, that means that it would take 1/2 of a second for the peak to reach this point at x equals 1. So it has to travel a distance of 1.5 meters, and it does that in 3 seconds. And so using this equation that is much more helpful than I've given it credit for, make it a bit more obvious there. You can find that it takes 1/2 of a second, or 0.5 seconds, for the peak to reach this point. So I'll make the end of this line up with t equals 0.5. And so this peak is at a y value of 3. And so I'll match that here. It wasn't quite there. I'll match that here. So the peak value, or like the y value at the peak, I should say it that way, the y value should be the same. Because the y values, both of these vertical axes on the history graph and the snapshot graph, so on the time graph and the position, like x position graph, the vertical axes are both y, so they should have the same value. Excuse me. So there's that first kind of line segment, I guess. Let's look at the second one. So the second one is going to start at the peak, obviously, because that's the shape of the wave. And so let's see. So when the peak is at x equals 1, which is the point that we're looking at in our graph. This isn't necessarily right, by the way. I haven't finished this line. So when the peak is at x equals 1, which is where, like, what our peak corresponds to, the tip, or like the end of the wave, is 1, 2, 3 meters away. So if it's 3 meters away, it has to traverse or travel a distance of 3 meters, and it's traveling at 3 meters per second, then it'll take 1 second for this this point to go towards, or to reach x equals 1. I should put it that way. So it'll take 1 more second for this to reach, for the end of the wave to reach x equals 1, and it'll look something like that. Looks good. Okay. I want to try one more thing, just because I realized if we jump right into the third example I have planned, we'll it'll be kind of redundant, and I guess there's another type of case or another situation that I want to show you and practice with. So I want to redo this orange one, and I want you to do it for the speed of 1/2. Actually, I was going to write 1/2. I'll write it like 0.5 meters per second. So now on one of these other two graphs in this first row here, I want you to do the history graph for the point x equals 6 again, for this orange wave traveling to the right, but now it's traveling at 0.5 meters per second. Just because I want to kind of show what what difference the speed makes. If you change the speed, how will that affect the history graph? So give that a try on one of the other graphs that have x equals 6 written in the corner, and I'll give you a ready to continue message in the chat. Okay, that looks fantastic. So since it's traveling at 0.5 meters per second, it'll take 4 seconds for this first vertical line to get to the point x equals 6. So you have your wave starting at time equals 4. Perfect. It'll take another 4 seconds for the second vertical segment to reach the point x equals 6. And so you have your second vertical segment at time equals 8. And your connection between them. That looks really great. Yes, that's a really excellent way of putting it. In the chat, someone said it's a lot narrower when it's moving faster. Absolutely. The history graph will be narrower the faster it's moving and wider the slower it's moving. There's one other pattern, or not really a pattern, I don't know. There's one other detail I want to point out, in case you find it helpful to remember it this way, is that the orange wave that we were working with is traveling to the right. And so no matter what speed we made it go at, the history graph that we were looking at is kind of reflected, or the shape of the history graph is reflected. So in the snapshot graph, the original one, we have the taller part of the wave on the right, but in the history graphs, the taller part is on the left both times. So if the wave is traveling to the right, or like towards bigger values of x, the history graph will always be flipped compared to the original. Whereas in the case of the green triangle wave, it was traveling to the left. And so the history graph we did for this one had the same type of shape. We had the steeper line first at smaller values of time, and then the less steep line after that. And that will always be the case for left traveling waves and right traveling waves. So if it helps to think about that, you have to draw a graph like this or match a graph on a test or something, something that you might want to keep in mind. Okay, what about the far right graph? Okay, so this blue graph, yes, there's a big chunk of the wave is in negative y values. In the y versus t graph, in the history graph, but the blue one, we'll have the same type of thing. You can definitely have negative values of y for time. We're gonna get into some interesting things with this example, though. I'm not sure if that really answers your question, though. Like, yes, in the history graph, you can have negative values of y and have like a negative part of the wave. Is that what you were asking, or is there something else? Oh, does it get reflected? It would get reflected. It would not get reflected vertically. So these negative values of y here would not get reflected and become positive values of y. But if this wave was traveling to the right, then it would get flipped, kind of mirror image left and right. So the negative values of y will never become positive or vice versa. But instead of having this long line part of the wave on the left, you might have it on the right if the blue wave was traveling to the left. Perfect. Okay. Okay, this last one is going to be some fun. What we're going to do now is we're going to let's see. Let's make this wave. Make this wave travel to the right. And it's going to be traveling at 2 meters per second. 2 meters per second, traveling to the right. This is what the graph looks like at time equals 0. What I want you to do on one of these bottom graphs is sketch the history graph at x equals 0. And this is different from what we've done in the two previous cases, because x equals 0 here is right in the middle of the wave. So some of the wave has already passed and some of it hasn't passed yet. So this is what the wave looks like at time equals 0 and traveling to the right. So that can tell you about whether the image in the history graph looks reflected or not. And I want you to try to come up with the history graph at x equals 0. I'll put a dot there. Okay, so question in the chat. It says, I can see how the leg starting at x equals -4 gets to the point. Absolutely, because it's because this line segment here is just starting at x equals 0, and so as time goes on, this part of the wave will go towards x equals 0, and that part of the graph that you have down here looks fantastic. But what about the part at x equals 2? Okay, yes, it has already passed the point x equals 0. So this diagonal line, as well as the vertical one that just kind of excuse me, that just kind of finishes it off, this whole part of the wave has already passed x equals 0. So if you want to plot it in time, that would be considered negative time, just because this part of the wave that goes from x equals 0 to x equals 2, that passed through x equals 0 before this picture was taken. So this, I don't know, I guess I say the picture, like the snapshot graph at time equals 0. So this is at time equals 0, but this part of the wave passed through x equals 0 before that. So the way that we're working with time equals 0, this part of the wave would have passed through x before t equals 0, so that would have been in negative time. So it's the same type of process as we've done so far, but this part passed through x in negative time values. Okay, so the point at x equals 2 is at t equals -2 divided by yes, what you've written in the chat looks absolutely right. And once you've got it drawn on there, then I'll talk about it for the benefit of anyone else watching this. Okay, this looks amazing. Perfect, yes. So this looks great. So at x equals 0, the longer segment, like we talked about, it's starting at y equals -1, something like this, I guess. And since the wave is traveling at 2 meters per second, and this length here has to traverse a distance of 4 meters, then it'll take 2 seconds to go down to a y value of 0, which is what you have. And that's great. And I need to move a cat. And the cat did not want to be moved, but that's okay. So this line segment that I have, which is the same as what you have, this is showing what's going to happen as time goes on. But now, and this is, I guess, where the name history graph probably comes in, is that now we have to look at what already happened. And so we can look at this diagonal line segment here and say, well, at time equals 0, look at this point, I guess. At time equals 0, this point is 2 meters away from the origin, or it has already traveled 2 meters past x equals 0. And so since the wave is traveling at 2 meters per second, that means that it took 1 second to go from x equals 0 to where it is here at x equals 2. So 1 second ago, or 1 second before time equals 0, is where this part of the wave would have just hit x equals 0. So on the graph, we have this part connected here at this kind of bottom peak, and 1 second ago, sorry, because this point, or like this peak here, moved a distance of 2 meters, going at 2 meters per second. So 1 second ago, or 1 second before time equals 0, the y value was at a height of positive 1 meter here. And then we have one last line segment just to kind of finish off the wave, connect it to the rest of the string, or whatever the wave is traveling at. So this is the graph that we end up with. Let's do a couple checks to see if this makes sense based on what we've learned so far from the previous waves. So for one thing, we have a speed that's bigger than 1. And with a bigger speed, specifically bigger than 1, the graph gets squished horizontally, never ever vertically. The vertical, like the y values, always stay the same because it's the same axis, or the same axis on both graphs, but horizontally it gets squished. So here we have a speed that's 2 meters per second, so that's bigger than 1, and our graph is squished. So that makes sense. That's a good I don't know, like sanity check, I guess. So that's good. It's doing what it's supposed to. Also, the wave in the snapshot graph is traveling to the right. And so that's just like the orange graph that we dealt with first. And we saw with the orange graph that since it was traveling to the right, the image got flipped. The image in the y to t history graph. And so this blue wave is traveling to the right. Our snapshot, no, that is the snapshot. Our history graphs should be flipped, or the image should be flipped compared to this, and they are. We have the narrower peak here on the left and the longer segment on the right. So everything checks out. It has all the properties it should, and that looks good. So I think I will stop there for today. Tomorrow we'll be doing some more problems and that type of thing. And yeah, that's it for history graphs for today.